Hello guys, and welcome to this new episode number 6. Today we are gonna see a new RL agent on a new game. Yes, today we are gonna see the algorithm playing Street Fighter 3. Okay, so this is the main topic of today. Of course, as usual, use the chat to interact with me. It will be a great episode. So welcome to DIAMBRA. Okay, so let's get started with the today episode. Now, a super brief recap of what we saw in last one. 2 days ago, we started to watch RL Agent playing our games. We used a very famous algorithm. We used the proximal policy optimization algorithm on Dead or Alive ++. You can find that episode if you were not able to watch it online and in live. You can find it in our YouTube channel. All references can be found on the DIAMBRA website, diambra.artificialtwin.com. All episodes are listed in the dedicated playlist in that channel. And so in that episode, there are a lot of explanation about how we proceeded. So the type of policy network we used, and the approach we adopted. And of course, there are live runs of that agent. Today, we are gonna see something very similar on a different game. Street Fighter 3. Now, before diving into it, I will summarize main features of Street Fighter, of course, and even with the help of the common, now you should be familiar with it, the common window layout and graphics we will use to show you what is happening in real time behind the scenes. So this picture here, you should be pretty familiar with it. It's the standard window layout we will adopt. Hello Erchimau, it's great to have you here again. Happy to chat with you all. Now this reminds me hello Ale, it's great to have you here. I know you're particularly interested in this specific game, and so yes, it's great to have you. Also, I know you are very familiar with the game itself, and so let's discuss together what we will see. Now, back to the picture. You should be familiar with it. on the main window on the slight left here is a window showing you in real time what is happening behind the scenes for the agent, for our algorithm. So basically you will be seeing the algorithm playing on the left side, so as player 1. This algorithm will select its actions to be sent to the environment, processing the state of the game, and this will happen in real time. So state of the game is represented by frames, collection of frames. Hello, Curaro. As usual, great to see you. So 6 frames, and as usual, AI and com health, the character. We are using previous actions sent to the environment, as well as both players' side, meaning if they are on the left or on the right, and the stage number, as usual. Of course, during training, we also used, as you know, reward that is not used in inference, but will be displayed because it is our measure of how well we are doing. For Street Fighter, we have 8 possible difficulty levels. The standard one that we will be using is level 6. Now, there should be 10 stages, okay? A single run is composed by 10 stages. I said there should be because there is one bonus stage in the middle that is around stage 7. And so since I'm pretty bad at the game and I never took a look at the trained agent, I'm not sure if in our configuration this is the case. So if we have that 7th bonus stage, we will see. Of course, as you know, in Street Fighter, you can also have bonus stages in the middle, like on the 3rd. After the 3rd stage, you have the car to break down, but it is possible to disable these bonus stages, and this is what we will be doing. Okay. Now, as usual, let's first recall our baseline of reference. That is the random agent. Since when using reinforcement learning, the random agent is the baseline of reference. It's the level at which the random agent will start learning. This is what we use to evaluate if we made some progresses with respect to the starting point. So let's start from there. Let's start from a very quick random plays by the random algorithm. And I will just use 3 episodes. I believe, I'm confident it will be pretty quick. So let's see. Let's move to AI versus com mode. That is the standard one to let the agent play. Random mode, we have to select it. So we activated Street Fighter 3. As a game, we will be using Ryu, okay? Only Ryu that is has been trained on both sides, so playing randomly as a P1 or P2, and also using 2 different outfit color. So let's activate usage of the random player. It is just this one, and let's select only 3 episodes. Okay, this should be it. Let's see how we are doing with the random player. Okay, so this is the window where you will see the game going on. Now, okay, as usual, the system is selecting difficulty of 6, and then is automatically selecting also the character that will be Ryu in our case. you may be wondering, well, why is it going just on the right to select the character instead of going up? It would be way shorter, way quicker, but the problem is that this is a way to take into account, in a simple way, how to select the character. So let's start random agent. Let's enlarge a little bit. It's pretty usual, the way of play of the random agent. As you know now, you should be familiar with it. And the reward won't be high enough to say we are playing at a decent level. It will be pretty down, even if sometimes it is able to move to the, let's say, second or third stage, for example. As in this case, you see we are almost there to win the first round. And let's see. As usual, guys, if you have questions in the meantime that we are taking a look at the game, please don't hesitate. Maybe it is maybe useful to recall game features in this case that are slightly different with respect to Dead or Alive. In fact, in this game, we will be using standard 8 moves plus the no action move and 6 different buttons for attack actions. Okay, 6 different actions, so 3 different punches and 3 different kicks. Okay, so 6 attack actions plus 8 move actions plus the no action, it adds up to 15 different possible actions. Okay, we will be using, as in the previous episode, we trained our agent to use a single discrete action space, and so we will be using only 15 actions without the possibility of pressing together attack moves or pressing together move and an attack button. Now the random agent, as you can see, has a probability of choosing the given move 1/9 for the move action and 1/7 for the attack action in this configuration. This is the reason why you are seeing 0.11 and 0.14 has a probability. Okay, so we are at the second stage. And you see a cumulative reward now is 1.71, 61, now is around 2. We will see at the end level we will be at. Now, an important thing is, you remember Dead or Alive was a trained agent with that played for around 57 million steps. Okay. In this case, this one is we will use a trained agent that played around 100 million steps. So Ale, first question from the audience. Ale is asking, the comments are all consecutive. Okay, you know, in Street there are more moves. There are moves which use multiple buttons altogether, and you are right. Buttons combinations are not, let's say, available for this configuration, in which we only made available independent actions, so move or attack, and no attack buttons pressed together. And so it is maybe possible that some moves are not admitted and are not possible in this configuration. It may be something that can be a specific limitation of this configuration. Of course, on one side, this limits our agent. On the other side, it makes our task easier because we don't have to choose, our agent doesn't have to choose among a huge set of possible actions. So it is in some way a more simple condition, since the space, the action space, will be smaller, and this in some sense facilitates how our agent is trained. Okay, we just lost our episode with a total cumulative reward of minus 0.05. This is our first episode. Let's see if it will be fast enough, or we can even stop at 2 episodes. Ale, I'm not sure if I answered to your question. Otherwise, please help me understanding what is your... okay, thank you, perfect. You are saying, and that was answered. Great. Thank you. Now, second episode. Let's see. The first one, cumulative reward of around 0. Remember, the entire full health bar is equivalent to a reward of 2. So if you perform 2 different perfects, you obtain a cumulative reward of 4. Another important thing to notice is that in our additional info, that are additional variables provided to the agent apart from frames, we are not providing time, so remaining time or elapsed time. And you see the bottom of the screen, there is a bar that shows, now is showing max for both players, and that bar basically is related to the availability of charge to perform some moves. That information is not provided to. Okay, so all is the agent is receiving is what is represented on screen. Now we are at stage 1, and we won the first round. And let's see now if we're able to land the second one or not. Today I will try to keep the live a little bit shorter than the last one that lasted for about 2 hours, quite a lot. But it was the first time we were streaming reinforcement learning agent trained, so their episodes lasted way longer than random agents, of course, and so it was not predictable. So you saw now our opponent Scene was able to perform a special move, having that charge bar full, and so he won the second round. Let's see how the third one goes. So far we have a reward, positive cumulative reward of 0.4. Let's see where we will set ourselves our performance at the end, and then we will be able to move to the reinforcement learning agent. I will show you the policy network architecture has done in previous episode. The architecture will be represented on screen. If you want, we can go into some details. A lot of things have already been said in a previous episode, and so again, now we lost our match. And so again, now it's a reward of about 0.0 for this episode. So we are in that range. It's pretty clear, okay? I believe we can stop now instead of waiting until episode 3, because it's pretty clear the reward is around that 0 point something. Okay, so time to move to the reinforcement learning trained agent. Let's activate it from the script, and before moving to it, I will answer another question. Of course, I will show you this picture that is a recap of our policy network. So Marco is asking, is the number of variables important for the selection of the ML algorithm? For example, some methods are not performing well with plus 100 variables and so on. Well, this is a super interesting question. Thank you, Marco. This is something that in some sense involve a lot of different aspects. There are many different RL approaches that basically relate with, for example, strategy on policy and off policy methods, methods that are built on the so-called actor-critic duality, genetic algorithms, for example, inverse reinforcement learning problems, and let's say all these different methods have, as you can imagine, pro and cons. One important thing to take into account, and of course strengths and weaknesses, that depends on the problem itself. Now, in this particular case, you see, the point is you have to be able to find a good representation of your state, of your problem, and so treat your input variables that are representing the environment appropriately. Now, think about, in this case, we are seeing on screen. Information contained in frames is basically composed by 256 by 256 by 6, and this is the total number of integers you are using to basically represent the screen. Now, this is a huge amount of numbers, but appropriately processed through, for example, a convolutional neural network, they, at the end of the process, reduce to 512 numbers. So it is not just a matter of number of variables, it is also nature of them, it is what they represent. It is a good way, the key point is, one of the most important point is the best way to compress the information contained in those variables in order to be accurately represented with a treatable number of features. In this case, you see, we are proposing the very same architecture we used in the other game, in the other live. The first reason is something that works, is the first thing to try. When you transfer it from the environment it demonstrated was able to solve in a new one. Okay, you can start from that baseline and then improve it from there. Now, you see here basically same structure, only two different numbers. The first one is additional info, moved from 161 to 197, and number of actions probabilities from 12 to 15. Both variations are obviously, in this case, in the case of actions, related to the number of actions available. So since we have 15 possible actions, we have 15 action probabilities related to them. We will select the action with the highest probability. Okay, this is the argmax. At the same time, the vector describing previous actions is a vector that represents all actions that has in particular last 12 actions performed by the agent, by the algorithm. So since we are representing not 12 as in the other life, but 15 actions, this is the reason why the number of additional info increased from 161 to 197. Okay, so the architecture is the very same. The algorithm is the very same. Basically, almost everything is equal, apart from, as I just said, number of actions, and so this slightly changes the number of inputs and number of outputs. Actually, the second last stage before getting the final output. Okay, so this is what is behind the RL agent. Marco is asking another question. So now you're working on a single objective optimization task. Is your RL algorithm possibly used in a multi-objective approach? Super interesting question too. Thank you again, Marco. You know, we are trying, what our agent is doing is trying to maximize reward. This is what the main target, the main goal of our algorithm. The reward is our main measure of performance. So what we are doing is maximizing it. Now, how you shape your reward is a key point in reinforcement learning. Shaping the reward is where very important things happens, and you have to be really careful, because it is usually a very important piece of your entire algorithm. So as you said, in this case we are optimizing the amount of health we are able to obtain by hitting the opponent, and at the same time we are trying to minimize the amount of health the opponent is able to lower in our own levels. So the point here is, this is the only objective now, but by simply appending to this specific piece of your reward something else. For example, if you add a penalty to it by adding, for example, the time elapsed, or maybe subtracting the time elapsed in your round, this would be let's say a penalty towards those agents, those algorithms that are slower with respect to others. So the agent will be, let's say, encouraged to finish the round in a quicker way. Okay, so there are, of course, you have to take to be really careful when you modify this kind of stuff. Another way can be, for example, had the penalty when your agent is, for example, trying to hit his opponent when the opponent is clearly unreachable by his plays. So there are a lot of different modification that you can add, and of course it should be clear by now, you can shape it to take into account multiple objectives. And so the answer is yeah to your question is yes, you can use it to in a multi-objective problem setting. Let me know, Marco, if you have more questions. Now that we took a look at the network architecture, we can start our PPO algorithm. Let's see. Okay, PPO is already selected. Let me change max number of episodes from 3 to 5, and let's execute it. Okay, thank you, Marco. Always nice questions. So I have to be honest, I basically never saw this agent in the game and at the inference stage, and so we will together get to know it. Basically, I stopped training like few hours ago, So I let it run until today. It reached 97.5 million steps. And so we will see how it will perform. It is the very first time I'm taking a look at it, you know. So let's see together what we can say about, what we can notice about the way it will be playing. Let's start. Okay, it seems that it is starting to, let's say, do something specific, meaningful at least. So trying to hit. So far we have been never hit by the opponent. That is now, oh, you see that it was when the agent noticed that he was having like ducks around his head, he tried to approach him more quickly. It seems that he got it somehow. Let's see. So first round was a perfect, not bad as a start, but as you know, it is not so easy when you move to other stages. So let's see. Come on. Okay, 2 perfects. Not bad. Let me say not bad. Oh yes, of course. Sorry about that. Let's grow the screen so you can see. Okay. So let me know, is this size okay? If you want it, I can try to make it a little bit bigger. Okay, so stage 2. As usual, please remember that the stage we reach is not the only thing that we should take into account. Actually, it is not the first thing to take into account in order to evaluate if the agent was good or bad. The main thing to take a look at is the total cumulative reward. Okay, that is what we are maximizing, and so that is what we should look at in order to identify if our algorithm is improved or not. So far so good. I believe that we are performing pretty. You see that? Okay, this time it didn't try to reach the opponent under that condition, that stun condition. Okay, second stage is gone. Let's see. So far our total cumulative reward is 7.06. A good one for now. Remember that the random agent was 0.0. Okay, let's see now. Third stage. One thing that I should note maybe is that the agent is trying to only hit the opponent with how should I call them, standard moves. So no, for example, attacks from afar like Hadouken, this kind of stuff. The agent is just trying to hit the opponent with punches and kicks. Nothing, let's say, fancy, just standard moves. This is at least what I'm noticing right now. Nevertheless, it's, I mean, obtaining a good performance. So as I said at the beginning of this live, the level of the opponent is 6 out of 8. Okay, and we also passed stage 3. So again, I just transferred the architecture from what was performing in a good way in the other live. I transferred the architecture of the net in Street Fighter. I started from scratch, training from scratch in Street Fighter. Maybe the opportunity of using an already trained agent can be something to leverage in order to speed up training. You have to appropriately take into account different aspects like observations space and action space dimensions, because of course if your agent is taught to let's say take into has input a given dimension of frames of additional info, and if it is conceived to provide in output 1/15 possible actions, you cannot change these numbers and expect it to work smoothly. You have to accommodate this modification, maybe saving weights, for example, or parameters values only for those network layers that can be thought as common layers between the two different models. For example, we are using the very same feature structure from frames, meaning that the convolutional neural network extracting features from our collection of 6 frames is the very same. So we could use, for example, as a starting point, network weights obtained by Dead or Alive. That can be an idea to speed up this training. Okay, so we are at stage 5, I believe. Yes, stage 5 with a total cumulative reward of 11.24. Let's see where we'll go this REU agent for our first episode. I honestly don't think it will be able to reach the final stage, simply because, you know, first of all, this agent has been trained for less time than with respect to Dead or Alive on one side, and then at the same time it has a bigger action space. In fact, it has 15 possible actions, and with respect to Dead or Alive, it's bigger, since Dead or Alive was using just 12 actions. But let's see. Okay, so we won this stage 2, so we are moving to stage 6. I believe there are 10 different stages, as I told you. Let's see. Okay, 13.66. It seems to me that is basically already tried to enter the opponent defense using like jump plus hit in some sense, and then trying to hit him from a close position. So you see that it's trying to reach the opponent in that way. Combination of jump, hit, and a close hit. Okay, first round is gone. Please remember that the random agent was performing like with a cumulative reward of 0.0. So, you know, pretty sensible difference also in this case, as we saw in Dead or Alive. And also another thing to remember is that we never scripted combos in this game, so if the agent wants to use them, it has to learn them by random chance, executing them by random chance, and being able to link the fact that that combo provided a good result, and so on. Yes, Curaro, you're right. I noticed this too. So he's using most of the times the punch when jumping, while me too, when playing, I used a lot kick instead of punches when approaching the opponent with the jump. So yes, it's strange, kind of strange, I know. Apparently it in its experience performed inside the game, that was a good move. Let's see, we are almost at the point of a critical point. Let's see if we are able to land this one off. not? Oh, yes. So we are moving to stage 7. Oh, Marco is noticing that once the player is hit by the opponent, it stands up and tries to kick, as Kazumi was doing. I believe this is just a coincidence, and I will take a look at it. Let's see. Yes, it's as Kurari is saying, it looks efficient because without doing fancy things like strange moves and these kind of things, it performing, let's say, good. We are at stage 7 out of 10 or 9, 10 or 9, and so it's not so bad. Okay, now we got a really bad bit in this one. Let's see how we will be doing. Maybe we can run another episode or two. They are pretty long, I know. This is the reason why we should be, running these things continuously, because especially when you have to evaluate long runs, you have to place workers in parallel and in order to speed up not only training but also evaluation. Oh, careful. Oh, come on. We're almost there. We are almost done in our episode. Yes. Okay, this one ended this way. So total cumulative reward for episode number 1 is 12.46. Okay. Maybe we didn't reach the final stage. We ended at stage 7, but I believe it's pretty evident that the random agent is performing way worse than our RL agent. So it's clear that this approach is able to build algorithms that are then capable of playing these games, and so approach these environments in a very good way. Please remember that this algorithm has not been in any way pre-scripted, so it has no pre-scripted combos. It just was just playing randomly and learning from it. Okay, so it's a really powerful way of creating programs, because these algorithms are in some sense programs able to program themselves to perform a specific task in an optimal way. And this is a powerful concept, probably the most powerful concept of reinforcement learning. You just insert rules of the game, rules of physics, laws of physics, and you let the algorithm do the job by just interacting with the environment, understanding what performs in a good way, what performs in a bad way. The agent will learn how to script himself to optimize the goal, the final goal, that is the reward. So we just passed stage 1 in this second episode. As we did with Dead or Alive, we can try to see if I'm able to beat this trained agent. We can try to see how this trained agent performs with using a different character, for example. We can try many different things. Once you have your trained agent, you can, of course, perform different experiments. Another possibility would be to let this agent face himself at a lower number of episode checkpoint for parameters values. So these are typical experiences and tests that can be useful to better understand how everything works. Let's see now where in this second episode where we will be, at which level we will land. Okay, Curaro is asking if we are able to let the agent play against himself. Now, it should be feasible. I have two doubts about that. The first one is, since, for example, in this case, Ryu never encountered Ryu during training, because as the game is thought to let you face different opponents than yourself, then this may, let's say, confuse the agent in interpreting frames. This is the first one. Hello, Belpargo. I'm really glad to have you here. Don't worry, as you know, the episode will be posted on YouTube, and of course, you are already seeing the proximal policy optimization algorithm in execution. Bear in mind that a random agent is around 0.0 has cumulative reward as a reference. First episode we run, we obtained a total cumulative reward of around 12, I believe. So, you know, it seems to be working. We reached stage 7 in episode 1 out of 10, I believe, 9 or 10. So a good let's say performance. Second doubt I have, Curaro, is that executing two different agents on player 1 and player 2 sides will double the usage of the GPU, and so I'm not sure it will be able to handle it. Maybe it will be crashing everything, but we can try. If we want, we can try. I never tried it, and so I should take a look at it, but maybe it can be something interesting. So let's I believe it would be interesting. I can try to do it. We can try to see if I'm able to crash down everything. Maybe it is interesting, you know. And as I already said in the previous episodes, also coding is something that I would like, coding session I would like to share with you. So it's another thing that it's interesting to share in lives. Okay. Let's see, now we are at stage 4. Our reward is around 9.2 right now against Chun-Li. Let's see where Ryu goes. First round is gone. So just to recap a little bit, for those who are joining us right now, we used the very same policy network architecture, the one that we used in the other live. Very same idea, so a convolutional neural network processing frames, fully connected the neural network processing additional info, then concatenating together these values and providing them as inputs to a final fully connected neural network that at the end provides the action of choice. So the very same architecture, slightly different numbers because there are different numbers of so the action space is slightly different. In Street Fighter we have 15 moves, while in the other life we have only 12. But the idea is the very same algorithm, same or very similar, I believe, the very same set of hyperparameters. So as I was saying, I simply use the very same setup on this different game. Okay, so stage 5. This character here, Hugo, was the one that beat us in the previous run, but now we are facing it at stage 5, so it should be slightly less difficult to face. Let's see. Okay. So again, the typical approach here is basically Ryu is trying to hit the opponent with a jump plus punch and then some kick or punch again. Very standard process and procedure to try to hit the opponent. It did pay off in the first episode, meaning that we obtained a good reward, and so it seems. Yes, you are right, Curado. RL scripted himself. You are right, and this is exactly you know what happens. Well, it's important to keep in mind that the sides of our, for example, our policy network is of course fixed in this case, and is of a certain amount it has a certain amount of neurons, and so at the end it has a certain amount of parameters. So that basically is something related to sides. That means also in some sense power for the network. So of course it may be that a given size is not big enough to solve a problem in an optimal way. So for example, additional tests that can be done are creating a bigger network instead of using, for example, only 512 features for at the end of the convolutional neural network. You may need to create 1024 instead of 512. Same thing applies for the additional info, and same things applies for example, networks placed after the latent space, so the feature vectors. Creating bigger networks sometimes, of course, it slows down training. It is not automatic that you will get better performances, but it is definitely something to try. So you know, it may be that also that the level you reach is something that you cannot surpass with the very same architecture, especially with the same policy sides. You may need to change it. All these aspects are hard to, let's say, choose by heart at the very first attempt, and you need to perform, in some sense, a research. You have to, for example, perform what is called a grid search. For example, there are other possibilities, but the grid search is where you define your set of hyperparameters, and you define ranges for them. Specifically, you define maybe discrete values for them. Let's say, okay, number of neurons I want to try for this layer, I want to try 10, 20 and 50 neurons. In this layer I want to try again 10, 20 and 50, and then you evaluate performances in using all combinations of these things. Now, as you can imagine, this requires a lot of computational power if you want to obtain results in a meaningful time frame. Because, you know, for every configuration you have to wait until the training procedure has ended. So I told you I run about 100 million steps with this algorithm, and it took me about 1 month. Okay, in my small infrastructure, but it's 1 month, and this is with just one single configuration of hyperparameters. So let's say that I have, I don't know, 3 different hyperparameters, every one with many different combinations. And so let's say that at the end you have, for example, 100 different configuration for hyperparameters. You have to run 100 times training until it reaches the final, let's say, definitive level. And so you need to have computational power. Actually, this is one of the most important limitation of to make RL applicable in industry, let's say, and so making it something that can be adopted widely in many different fields. This is the so-called sample inefficiency, and is one of the most important limitation causing this problem. So you have to create a lot of samples to make the agent learn. Samples in our case means experience and game episodes, basically. So if we are able to lower the amount of samples needed to make the agent learn in a good way, this can be one of the most important breakthrough towards making RL applicable into the wild, let's say. Okay, we are now at episode 2, stage 7. We won the first round, we lost the second one. Let's see how it goes. It seems that we are almost there. We're almost there, almost. Okay, we lost this one again. Now, so both times we lost at stage 7. Okay, but both times we had a reward of around 11, 12. Okay, I can stop it right now because we are already at 1 hour of our stream. Now, let's see if I can show you the agent playing against himself. So, nevertheless, let's wrap up a little bit what we saw with AI versus COM mode. Random agent cumulative reward was 0.0, around that. Our RL algorithm reached 11 point something, more or less. That is clearly a demonstration that RL is working properly, is obtaining a very good performance. This confirms what we saw 2 days ago in the other live, and this can be considered a baseline for RL, a very simple, let's say, network architecture, and that I will provide together with the environments once they will be available, so that everyone that is going to participate in our tournament, where people from around the world will train their RL agent to make them compete in our tournament, fighting against the computer or fighting one against the other. They can start from there, seeing how a given algorithm is trained on this specific environment, and start from there to improve what I did, okay, to make it better. Now let's try to see if I'm able to let the computer crash. Okay, so AI versus AI. Let me select Ryu versus Ryu. Okay, has characters. Let me go down. I do have to select here PPO versus PPO. Okay, now PPO versus PPO means that we will be using 2 different algorithms on player 1 and player 2. Okay, it should be okay. Now get ready to see crashes. Let's see. It's kind of fun to test these things. Okay. I will keep an eye on GPU RAM usage. So we are about now 1.9 out of 4 gigabytes. Let's see. Okay. I will enlarge the window for the game. Just give me a sec. Okay, we are 2.9 gigabytes occupied. This should not grow bigger than that. Let's see. So Ryu on one side and Ryu on the other one. Player 1 versus player 2. This is actually the first try to letting two different AI algorithms playing one against the other. Actually, this is the first one. Let's see. Freeze a little bit and then they start. Okay, it seems to be working. So it's 3.1 gigabytes and that's fair enough. Okay, we are seeing the very same algorithm on both sides. You see PPO 97.5 million steps on both sides. This is working, and so this is the first time I'm trying it. Oh, come on. The one on the right is doing strange things to me. Oh no, it's moving also in the other direction. It's kind of strange. You see, it appears that they are doing the very same thing because they are seeing the very same frame, basically. Okay. So strange. Take a look at also probabilities. It seems that there are in some cases they are more or less on the same level. So okay, anyway, I'm happy it is working, and as you can see, it's working in real time. No, it's not having problems of inference speed, and so this is the demonstration that we are able to use two different AI models on both sides. This is what will happen when people oh, come on. I'm sorry, but it's so funny watching these stupid guys doing that stuff. Anyway, it seems that this is the first demonstration that we will be able to use. Yes, they are pretty stuck. Yes, super. Okay, this is interesting actually, because you know, in self-play, this is something that can happen. Maybe if we are using different characters, this won't happen. I don't know. Anyway, is interesting. Okay, it's like kind of a dance. I may try to, you know, put up some music behind it, maybe in post-processing the video. It may be funny. Okay, and yes. So a strange test, this one, super nice in terms of insights, because it let's say ring a bell when I will be implementing self-play. I will be, you know, I will need to take care of these possible like loops. Curaro, you're right. You're saying, I think that an improvement is to let the AI understand which character is at the end of at the start of each fight. In some sense, this should be already there, because the parameter here is AIP1 side and AIP2 side is basically 1 or 0 is 1 if you're on the right and 0 if you're on the left. Okay, Dom, hello Dom, I didn't know you were there. You're there. Great to have you together with us. Of course, he's saying this bad behavior maybe can be solved by adding the time as a negative reward, and of course this can be one option, of course. Yes, so that the character is let's say may be willing to move towards the other one as the time is passing, and that can be another option. So we are like playing against ourselves. I can yes, Curaro, I will do what you're suggesting, so changing the character on the right. Oh, what else if not double KO? Of course, that's it. It's written. No, yes, I will do that, Curaro. I would like to test one thing that can be interesting. Let me see. Okay, as you can see, I will show it to you pretty soon. We have a few checkpoints that I saved of this network. You see here. So we were using this one, 97.5 million steps. I will try now to use this one on one side and maybe the 21 million on the other side. Let's see the difference between these two characters. So in that case, they won't be the same algorithm playing on both sides. And let's see what happens. Okay, I have to change the code a little bit because in particular here we have a running ADX for player 1 and player 2. So okay, I have this one, training epoch. I have to set it for player 1. I can just simply do something like, for example, let me think, training epoch. I wanted to do something more clean, but that's another problem. If edx is equal to 0, let's use this one, else I will use Curaro is saying Ryu dance can be the new obsession for this summer. I will I think I will try to make a video with some music. It will be fun. Okay, so the other one I select 21 millions. Okay, 21 million steps. So I'm shifting between Python and C++, so I may be missing something, not sure if this is right, but anyway, the system will tell us. It should work like that. Let's see. So now we will be facing with the 97.5 million steps player, the other one. So actually, we are running a little bit late. It's 1 hour and 10 minutes so far. But since you are so nice with me being here for all this time, I may think of a little surprise at the end. Maybe we can try to start, since from today, I think I will start training agents for Tekken. And so maybe we can try to start this process together right today. Try to, let's say, start the process of training together. It will involve a few crashes, a few tests. Let's see. Okay, now. So it's Ryu again against Ryu. 21 million against 97.5 millions. Go. Freeze a little bit and then Yuki. Okay, you see here it's on the left PPO 97.5, on the right PPO 21 millions. Let me enlarge this a little bit. Let's see if there are differences between the two. From these first phases, it seems that the difference in steps, training steps, it's kind of emerging from what we are seeing, at least in terms of health of the first round. Maybe, do you have... Oh, okay, I see what you mean, Kuraro. You're saying that it appears as if both characters are thinking they are on the left side. In some sense, it seemed to me, yes, it seemed to me too. But on the other hand, I trained them randomly on both sides. So I'm thinking, why would that be the case? I'm not sure. Not sure about it. Maybe something that can be revealing in that sense can be to use the train agent on the right side. Oh, also you're saying the outfit can play a role here, but again, as for the side, also the outfit was chosen randomly. So I don't know. You know, a lot of questions because the taking care of these things is not so easy. It's not straightforward. It's not something linear. You know. Anyway, it seems that the agent trained for 97.5 million steps. It's way better than the other, as one may expect. Okay, so I believe that, I don't know if you have any additional request, if you have something you are curious about and want me to try, just let me know. Okay, oh, interesting stuff by Kuraro. He's saying, let's switch sides. Let's make 21 million steps player play on the left. Okay, so you really want to prove me wrong, right? Didn't you? Okay, so let's see. It is, I mean, not unusual to find these strange behaviors. Oh, don't worry, I was just joking. Okay, so like an RL agent, yes. So training epoch 21 on the left and training epoch 97.5 on the right. Let's try this one. Okay, we had in the configuration we were using before, we had more or less one entire round of advantage, a reward for the left agent that was around 2, so an entire health bar, meaning one perfect round. Let's see now, switching sides, if this is the case also in this configuration. I'm curious about it. Let's try a few runs, 1 or 2. Then if you want, I can try to show you how to move from training Street Fighter to train Tekken. Maybe just a few initial steps, because first of all, if you remember when I presented the game, the environment is kind of buggy, so let's hope it will work as expected. I did a few tests with it and it should work well, but let's see. I got you. Now let's see the start. Okay, freeze a little bit. Yes, they are trying to do that, but okay, the player 2 is performing better, I think. Maybe there is they're switched sides, and so now let's see. Okay, player 2 won. Not, let's say, in a super fancy way, but Let's see now. Okay, please take into account that there was a bug, so it is totally possible that there are bugs. Okay, now player 1 won. It is totally possible. Anyway, let me say that running just 2 episodes, it is not so, in some statistical sense, meaningful. You have to execute a lot of them to have a sensible amount of data that allows you to, let's say, decide if the difference is meaningful or not. Anyway, as I was saying, I found a bug when we were presenting the game, so just few weeks ago, while the agent was already doing training. So I corrected the bug, and at that point the reward, the cumulative performance, started to grow way better. Okay, so player 1 won this time. Let's see another single episode. So for this one, yes, he won. And now so it is totally possible that there is a bug also in this case, maybe. But anyway, it is something that it shouldn't be there, meaning that yes, very interesting behavior. And of course, you know, something that has to be taken into account, and in order to do so you have to watch your agent play, because you have to understand this kind of stuff, and it's hard to almost impossible to infer this kind of trends only from numbers. Even if you can add a lot of charts, you can plot a lot of variables during training, still our human ability to extract information in a very performant way is something that you should take care of. Okay, so player 1 has won also this one. I'm thinking that some way there is kind of bias towards player 1 position. Let's maybe. One additional test that can be performed is letting the trained agent a lot of times only on player 1 side against the computer, and only on player 2 sides, and then comparing their performance. You say, Arcuraro, that you think they are both recognizing themselves in the left Ryu. Maybe. Anyway, the problem here is that okay, we can stop it right now. You know, the problem is that it shouldn't be so, meaning that I used a random choice for player 1 and player 2, so I cannot figure out right now why this is the case, if it is. Okay, so let's super wrap up now, super quick. We saw the RL agent in Street Fighter. As the one in Dead or Alive, it demonstrated that it was really good. And if compared to the random agent, if compared with it, random agent was at the level of 0.0 in terms of cumulative reward. Our RL player was around 11 or 12. It was another demonstration that the approach we adopted is successful. In other words, we have been able to learn how to play this game way better than the random player, obtaining a very interesting improvement with respect to it, and achieving in our 2 episodes stage 7 out of 10 at a difficulty level of 6 out of 8. This also demonstrates that these environments are learnable. Using only pixels, using additional info, these environments can be learned, and so this confirms that we can continue the pursuit to our main goal, that is letting people from all around the world train their own algorithm and then make them compete in our tournament. So Curaro is also noticing in these last AI versus AI matches that it seems like there is a kind of bias with respect to the player 1 position. So, and this shouldn't be there, but it shouldn't be so, but it appears there is a slight bias. Hello, Andrea. It's great to have you here today too. Don't worry. Now, okay, we are almost there. 1 hour and 23 minutes so far. Let's see. I wanted to share with you. Maybe it can be interesting to share with you one other thing. It's so far I've been training both agents, both on Dead or Alive and on Street Fighter. Next is, I think, Tekken. So I will be working on it, and so I thought maybe I can start to work on it right here. Let me see. In order to do so, I can go in our dedicated folder. In order to, let's say, make it more readable for the audience, I have training procedure in Python notebooks, not in Python scripts. So this is not optimal for some reasons, but it is way better to present what we are doing. Okay, let's start the Jupyter notebook in this folder, and let's open the script that is using PPO with a custom CNN, using a basic learning, so starting from a random agent in discrete action set and no attack button combinations. This is our training script. So let's clear the kernel. Now, okay, in order to do so, in order to use the very same approach, I will start to modify the script right here. So basically, where we select the game on which to train our agent is here, game ID. Now this automatically will create directories where to save a tensor board in order to plot our variables, as well as model checkpoint used just so. We are importing here our PPO algorithm is from here. We are importing our custom CNN policy. The policy network I shared with you before, it's a custom policy network that I built, basically fusing frames with additional info. A question from Belpargolo: will you keep also this part in the YouTube video? I'm leaving, but I would like to take a look at your code. I will keep it, of course. You will find it in YouTube video, so don't worry. See you next time, and thank you. So let's now continue. We have to select and to set different. Bye bye Belpargolo, see you next time. So as you can see here, there are a few arguments that you have to set appropriately. Some of them are just path. Okay, this one is interesting. This basically allows you to disable rendering of your environment. If you use false, this makes the agent play a game without rendering the screen, and this speeds up training quite a lot because it speeds up execution. Now you see here, this is what I was saying before, we are selecting player 1 or player 2 side randomly, so we will be playing half of the times on player 1 side and half of the times on player 2 sides. Now this is where we have game dependent keywords arguments, and in our case, since we are using Tekken, that this is the game ID. Difficulty of Tekken, I believe we were using 6 out of 6 out of 8, I'm sorry. We need to prescribe 2 characters, because if you remember, Tekken had 2 characters per side, and so I will be using Jin as first character, and Yoshimitsu, I cannot remember how is it spelled, so let me take a look. I can find it right here. This is our solution right here. It's Yoshimitsu and Jin. Let me select them, and let's see if I'm able to share with you this thing quickly. Jin and Yoshimitsu. Okay, so we will be using these 2 players here and here on both sides, because we will be using both player 1 and player 2. Character outfits 2 and 2, that's fine. Difficulty should be 6, I'm almost sure. Let me check. I have it here, and it's 6, yes, as you can see here. Okay, now okay, these are other keywords for other specific methods. As you can see, we are specifying that we will be using a discrete actions space, so move and attack buttons together, and we are not using attack buttons combinations, so pressing together punch and kick and these kind of things. We are not using that. Now we are specifying here in some wrappers that our frame will be of this size, 256 by 256 by one channel. So we will be using grayscale images. We'll be normalizing rewards. We are stacking 6 frames together. We are scaling everything. This is a parameter that I won't go into details about it, but it involves how you delete your frames, meaning you are taking every frame, 1 every 2 frames, this kind of stuff. In our case, we are taking every frame, and then this is the list of keywords that basically define our additional observations. What we will add to be treated as inputs to the frames we already have. So we will be using actions, of course, the actions buffer, opponent health, and our own health, our own position, our Take a look at this one. I told you bugs are always there. This anyone from the audience that knows what should be here? Anyone? Let's see if you are paying attention. What do you think is needed here? If we have own health, yes, you're right, Curaro. Here we should use opponent position, and this may be one reason why we're observing that behavior. So super cool, because I believe that this is something that I used also with Kazumi in Dead or Alive. So maybe this is something that can be limiting our performance, and I may try to restart training using this fix. Oh, you see, you know, maths, informatics is something that, you know, there is no opinion. Okay, there are no opinions in general. If it is supposed to work some way, it has to do it. You know, if it was doing something strange, we noticed it. In Curaro in particular was bugging me with it, and there is the reason, you know. And so this is something that always is confirmed by experiments, by experience, and it's kind of, you know, rewarding to note that things do not happen just randomly. Okay, so yes, we just fixed a good bug, and luckily I was here showing you these things, because these are those typical bugs that are hard to find. Now, this is another important parameter, number of environments. This is the number of environments you run in parallel while training your algorithm. So in this case, you see 8. This means that at this stage, the system will spawn 8 environments in parallel. Okay? Let me show it to you. Let's use the rendering in order to allow for a more meaningful representation. So we are just booting everything up. Now you see we are using, let's use 4 environments. Now remember that Tekken is kind of a buggy game, and so let's hope I was able to fix that specific bug that happens at startup. Let's see. Okay, we have 1, 2, 3, and 4 environments. You saw that. Let's use this ultra wide screen in the for the reason why it has been conceived this way. Okay, you see the environment always crashes at this point, and it seems that is happening again. Okay, so no worries, I will handle it. You should work with just a single environment. Let me see. I will take care of it, but we can try. I would like to show you what is like using multiple environments. So I will use Street Fighter, or maybe Dead or Alive. Let's see. Now let's see if it is working with only a single environment. Tekken. It is at this point the very first start that is having problems. You see with this video, basically it is having problems and usually crashes at that specific point. Yeah, that's the case. I will take care of it, no problem. Let me see. I can show you Street Fighter in order to, let's say, giving you an idea of basically how it is trained with multiple environments. Okay, so let's comment this one. Okay. Okay, and finally, let's run this one. Okay, this is of course the single one. Okay, let me use 4 different environments. So it's basically loads 4 different instances, 1, 2, 3, and 4, and the game goes here. Now it was stopped because we need to go on observation spaces and action spaces. You see, for Street Fighter, okay, Kurari is asking why 4, 1 per CPU core. Actually, this number of different environments is another typical hyperparameter to use. In fact, it's in some sense it influences how the training process will go. Of course, the more environments you have in parallel, the best speed up you will get in terms of collecting samples, so experience from the environment. I'm using now 4, but I usually use 8. I'm using 4 just to keep the load down in terms of CPU, but mainly GPU. So as you can see here, the action space is 15 for Street Fighter, as we were saying before. Then here we are, for example, defining number of layers of our specific network. As I showed you in our very first minutes, our architecture has 64 layers here, and so this is what we are using right now, this number, and you see this is 197. This is the number of additional info we are using. That is the sum of the action buffer length times the number of actions, move and attack actions, plus the number of additional observation we listed right here. Okay, we are not using this one, but we are using this 5 together with the actions buffer. So health of both sides and position of both sides and stage. So this is the number of info, and now here is where the model is loaded or instantiated for the first time. As you can see, it's the PPO. We are loading. In this case, I will be using 97.5 millions. This means that we are restarting from a given checkpoint. We are setting few typical hyperparameters to set, like gamma, that is the discount factor, learning rate, that is a typical hyperparameter to set, clip range, that is another hyperparameter for our PPO algorithm, and so on and so forth. In this case, we are scheduling a linear trend for learning rate and clip range. For example, in this case, it is moving from 5.0 by 10 minus 5 towards 2.5 10 minus 6, and this linear schedule is spread among the total number of time steps that I'm setting right here. Total number of time steps is 20 million. So I'm performing basically chunks of 20 million training steps. In these 20 millions, I set starting and ending values of the learning rate, clip range, and so on and so forth, so with a linear scheduler. Guys, instantiate your model or load it from your checkpoint. A quick display of model discount factor. Then make it learn, as you can see. So train the agent for 20 million steps. This is a save callback, pass it to the function in order to save every 1 million steps. And at the end, save the model. That's it. You know, you see in this half of a page code, you start from loading the environment, setting some variables, loading your model, and training it. That's it, nothing more. It's all contained inside this function. Of course, as you may understand, behind the scenes there are a lot of additional things. I would like to, I'm not sure I can load this one and let you see what happens, because I believe that this will saturate the RAM of the GPU and will give us problems. I could try it with one single environment, but I do prefer to avoid problems at the end of this live. So anyway, this is it. This is the way in which you train your RL algorithm. Okay, this I will also share with you maybe behind the scenes, meaning showing you where the policy is coded. I can do it pretty quickly, then we will go into details another time. So I coded my custom policy, as you can see, it's right here. Custom CNN policy, and is this one. You have a custom policy that is derived from an actor critic policy. And here you define your initialization, where you have your frames, you have your observations. And first of all, you divide them between frames and additional inputs. Okay, as you remember in our scheme, there are frames, there are additional infos, these two things treated separately, frames treated by a CNN, and additional info treated by a different fully connected neural network. Then they are concatenated together, as you can see here. So extracted features from frames and extracted features from additional input, they are fused together and passed as input to a new network that is defined right here. And so that's it. That's the policy network, the custom policy network. Here you can do your tricks and magic inside this one. This will be loaded into the script we just saw. And so you can do, you know, you have frames here, you have additional inputs here. You can do whatever you want with them right here. Okay, this is the only thing you need to do. And that's it, you know, this file ends here. Okay, so pretty simple and pretty straightforward if you don't have bugs like mine in my scripts. Okay, anyway, I believe that I'm not sure if you have questions about this, if it was at least the high level idea, if it was clear enough. Of course, these things, in order to be really clear, need to be explained with more slow pace, and I will do it. Today we are already at 1 hour and 45 minutes, so too long. It's too late to go into details. But again, guys, thank you a lot for being here, and as usual for asking questions. As you know, it's important that you contribute through the chat, because it's a way where a lot of value happens. Now, of course, Curaro, I totally agree with you that describing these things so quickly is not something that allows you to get what is working behind the scenes. But of course, we will dedicate the sessions to explain in detail this stuff. Thank you as usual, Curaro, Marco, Mau, Andrea. Thank you everyone. Thank you Dom for being here with us today. I'm glad you liked the Jupyter Notebooks idea. I believe it makes clear how to proceed step by step. It is a good way to show each step separately, and so that is something that works well. Okay guys, so again, it has been my pleasure to have you here this evening. I hope you had fun. I promise you I will make a dance video with those two reels doing that strange thing. I will find the appropriate music, and that's it. Okay. Again, thank you. It was fun today as usual, and so let's continue in this direction, and it will be really interesting and fun together. So today we completed another game run with a RL agent, and now we can move forward. I will keep you posted, of course, so follow all our social channels. That's the best way to keep the pace and stay tuned with our news. Thank you again, and good night all. Bye.